Okay, good afternoon, everyone. Let's get started today. I think we'll be able to finish up this unit. So we've been looking at the support vector classifier, which we can see it here. So we have this thing that we call the hinge loss, and then we have a term that looks like ridge, a ridge penalty. And what this does is it allows us to focus on the samples that are closest to the decision boundary and determine the decision boundary only from those most difficult samples. And we talked about how there's this parameter C that we need to tune. But anyway, we talked a lot about this. And the next thing to talk about is that so far we've only considered binary classification. So what do we do if we have more than two classes? So we know that just for generic multi-class linear classification, this is just totally generic. It's what we did with multinomial logistic regression also. What we do is we have k classes, and so we consider a score vector that has k numbers in it. And essentially, when we look at that score vector, let's say for a given training sample I, the largest, or the index of the largest value in it tells us which class we believe that sample is in. So the different values in here give us some sort of confidences on, how likely is it for that sample to be in each of the classes. So that's what we have. We have this score vector that has k elements, and the way that we make that score vector is we have a bias vector, which is going to be the same size, it's going to be k elements. We have a weight matrix. So in W, each of the columns in W, or the rows in W transform, correspond to a particular class of our k classes. So it's like we have a separate prediction vector for every class. We have a separate bias term for every class. And that's what we did before with multi-class linear classification back in Unit 5. Are there any questions about this before we move on? Okay. So the key question, though, is then, well, how do you train B and W? How do you train all those coefficients? And when we talked about logistic regression, we said that there were two ways to do it there. And very similarly, there's going to be the same two ways to do it here. The first way is to train the kth element of B and the kth column in W separately from all the other B's and W's. So essentially how you do that is you take your training data and you split it into class K and not class K. So you start with class 1, you split your training data in class 1, not class 1, and you train a binary classifier. And once you're done, you have the weights B1, W1, and you fix them. And then you split your data into class 2, not class 2. You train another binary classifier. You freeze those weights, and so on. So when we did this before, we trained those classifiers using binary logistic regression, and now we can use the same approach with binary support vector classifiers. So that's one. You could say maybe the simpler approach is just separately train these K, one versus rest binary SVCs. So the way that you train them is exactly by solving, by finding the parameters W and B that minimize the loss no matter how we write it. So it turns out that this is going to be a convex optimization problem. So it can be solved. We're not going to code it ourselves because it's a little more complicated than logistic regression, but scikit-learn can do that for us, and we'll see the code in just a moment. But that's one option. Okay. The second option is to jointly train all the B and W parameters all together. And we did that with multinomial logistic regression back in Unit 5. And now we can do it with an extension of our binary SVC that I'll describe right here, and it's called the Kramer-Singer extension. And I'll try to convince you that this Kramer-Singer extension, when you look at what happens when there's only two classes, it reduces exactly to what we were doing with the binary SVC. So I'll explain that next, but for now, are there any questions on these two approaches? These are really main things. Yes?
Sorry, actually, I think, is there a typo on your slide? Is that supposed to be Zi equals B plus W transpose Z, or X? On the,
So somewhere here?
well, yeah, so to the left of that, you have Xi equals.
That's all of
Oh, okay, I'm sorry, I'm just reading that incorrectly, that Xi belongs to the, yeah.
Oh, yeah, that's this
sorry.
term. So I'm just showing you here how these terms are the rows.
Yeah.
They're the rows in there.
Sorry, I was just reading that.
Yeah, it's all right. Okay. All right, so are these two options making sense at a high level? So in one case, you're using this kind of myopic view. Let's just train B1 and W1 separately from how we train all the others. So probably intuitively, that's not going to be as good as training them all together so that they all work well together, right? And that's what you tend to find when you experiment with these things, that this Kramer-Singer approach works better, but it's more expensive to do this optimization because it involves a lot more variables. But it's also a convex problem, and you can definitely solve it. It just, code takes a little while to run. Okay. All right, so any other high-level questions before kind of launch into the details here? Okay, so when you look at this, it's not so different from what we had before. So let me try to find, so like this is what we had before in the binary case. This is a vector, 2 norm. And you have a sum over the training samples, you have your C, and you have this max of 0, 1 minus yi zi. Okay, so now let's look at this. So instead of a single vector, we have a matrix. And we still want to sum up the square of all the terms in the matrix, so we do that with the Frobenius norm. We saw exactly the same thing in ridge regression with multiple targets. Okay, you could put the C over here, or you could move that C over here. So that's the same. We have the sum over the i's, just like before. So what's different is now, instead of the max 0, 1 plus yi zi, we have something a little bit more complicated. So, of course, we now have, you could think of Z as a matrix if you want. This would be one row in the matrix. The way we usually do it is we have a Z matrix where you index the training samples as you go down the matrix. So each one of these would be like one row in the matrix. So clearly we're going to have two indices. The first index on Z is going to tell us which training sample it came from. The second index is telling us which class we're referring to. So what we have here is when you are looking at sample I, you plug in the label, the training label, yi here, which is going to be one number between 1 and k. And then over here, you're summing across j for all the j's between 1 and k except for yi. Okay, so essentially that's it. It may not make obvious sense why this works, but it works. But let me at least try to convince you that when we focus on having just two classes, k equals 2, that this ends up boiling down to exactly what we were doing before. Now, you wouldn't really want or need to use this with k equals 2 classes because it's simpler to just use the binary version before where W was a vector, not a matrix with two columns. But you could use this for two classes, and it would give you the same solution. You mainly want to use this when you have k, 3 or larger. Then, of course, you can't use the binary method anymore. You need to use something like this. Okay, so let's take a look at this. So just to convince you that this is the same, for this little derivation, we're going to assume, rather than yi going from 1 to k, it just notationally, it's easier to think of yi either 1 or minus 1. So those are going to be the labels. And I know it doesn't make a terrible amount of sense to say, like, what's the negative 1th index, but we can just replace, just think of these as numbers. Instead of j being 1 through k, j is either 1 or minus 1, yi is 1 or minus 1. Okay, so if we do that, then, and we're going to focus on this inside term here. That's what this is. So I just wrote it exactly as it appears above. And now, let's focus on what happens if yi is either 1 or minus 1. That means when j is not equal to yi, j has to be negative yi. So this j I'm going to replace with a negative yi. Because those are really, if yi is 1 or minus 1, then when j is not equal to yi, it must be minus yi. So that gives us this. Then the next thing is we can write, we can see that there's really two possibilities. In one case, yi is 1, and this is minus 1. Or in the other case, y is minus 1, and this is 1. So these are the two possibilities, 1 and minus 1. And all that will change is essentially those signs. And so what we can do is we can have the yi here, and when yi is, like, let's say 1, then you're going to get a minus sign on zi1. That's what we expect. Otherwise, a positive sign on zi minus 1, and vice versa. So this is just another way of writing this. And finally, if we define a new b variable, which is going to be b1 minus b negative 1. So these are going to be the weights, the two different weights we have in here. And if I define a new w vector, which is the difference between the two columns in w, and I just give these names b and w, and we plug those in, then this difference of z's turns into this, which is exactly the hinge loss we saw before. So at the end of the day, when k equals 2, this is exactly what we were doing before. So just to kind of show you that there is a connection, it's the same in the binary case, but of course in the non-binary case, it gives us the option to do this joint training, and it works pretty well. Okay, so any questions on that? All right, so that's multi-class SVC. Let's talk a little bit about how we implement this stuff. So the main command in scikit-learn is called linear SVC. And it should have a form that's pretty familiar because it looks just like all the other regression and classification commands we've seen before. So I'll just tell you about a few special things. So first, when you instantiate it, that's when you tell it all the parameters. So for example, just like with logistic regression, you need to choose the parameter c. C is like an inverse weight. So as we discussed, larger c means fewer support vectors, up to a point after which increasing c doesn't do anything. Now for multi-class, you can either put in Kramer-Singer or OVR, one versus rest, just like we had in multinomial logistic regression. We had similar two options. There is an interesting thing about the loss. There's this hinge option. And this is actually the thing that we described. But strangely, or maybe surprisingly, this is not the default option. The default option is to actually use a squared hinge. So let me show you what I mean by that just in terms of a picture. So here's the picture we had with the hinge, like this. So a squared hinge would look like something like this. Okay, so it's quite a bit different than the hinge loss. So any guesses why we might want to use that instead of the regular hinge? Yes. This loss is differentiable, just like the logistic one, and unlike the hinge loss. And it turns out, when you do numerical optimization, non-differentiability ends up giving you a penalty in terms of how fast the algorithms can converge. So with this squared hinge loss, it's just easier to optimize, it goes faster, but at least in all my experiments, I found that there's a penalty to the performance. When you go from hinge to squared hinge, the answers you get are worse. So there's that trade-off. It's a speed versus performance trade-off. And for whatever reason, scikit-learn takes the squared hinge loss as the default, and if you want it to do the regular hinge loss, you have to tell it explicitly to do that. And you do that by writing loss equals hinge. And now it will use the standard hinge loss. And it will run slower and work better. So I just wanted to see how well we could do on MNIST with the best loss, hinge, and the best training, Kramer-Singer, to see if we would in fact do better than our multinomial logistic regression, which is what we tried last time. And it turns out the accuracy we get is 90.7%, which does outperform logistic regression by 0.5%. So what do you think? Is that exciting or not so exciting? What's your feeling? Not so much, right? After all this effort that we spent, like all this time lecturing, all this math, and then all we get is this 0.5% increase. It's a little bit of a letdown, right? It is better, so that's good. But so we're going to address that in what we talk about next. But before we do, just one other comment. There is another way to implement this. It's called svm.svc, which is actually what we'll talk about next. And there's a special case of this where you set the so-called kernel to be linear, and it will solve the same problem. But the algorithms it uses, the formulation it uses is different, and it runs slower, especially when there's a lot of training samples. So if you're trying to do this support vector classifier, SVC, and you have the choice between these two, I would recommend doing it with the linear SVC because it will run faster, but at least if you let it run long enough and all that, they'll give you the same answer. Okay, so that kind of concludes what we're going to say about the SVC. Now, we're going to start talking about what's maybe more exciting, which is an extension of it called the support vector machine. And it's really going to be directly based on the SVC, except we're going to use a couple tricks. The main trick is feature transformation. So this is something we've seen many times throughout the course. We saw this way back in Unit 1, where we said we had engine size versus miles per gallon. We said, oh, actually, if we try to predict the inverse miles per gallon, all of a sudden it worked better. And we saw this various places where, polynomial, you could say polynomial regression is sort of like non-linearly transforming your features by putting them to different powers, taking them to different powers, and then running linear regression on those, and it works a lot better than just linear regression, right? So this is, again, in the same spirit. But now, since we're dealing with classification, our objective is to do some sort of transformation so that the data is linearly separable or closer to linearly separable. So this is just a very kind of simple mock-up of this idea. Imagine that, let me try to relabel this. This would be like your raw features. These are the ones that you're given when you download the data set. and then we'll call these the transformed features. Okay, and you can see that in the raw feature space, there's no way I can pass a line through those features to linearly separate them because the data set is just not linearly separable in the original raw features. However, if I can do some transformation, and usually that transformation is going to go from a lower dimensional space to a higher dimensional space, here we're going from 2 to 3, perhaps after that transformation, I can pass a plane through here and I can perfectly linearly separate my data, or maybe not perfectly, but much closer to linearly separating. And that's the goal. So we want to do that. We want to figure out how can we do this, and we're going to use this notation for the phi will be the notation for the transformed features. So instead of using x, we're going to use phi of x. But the challenge with this is if I transform my features and I increase the size of my space a lot, then I have a lot more features to contend with. Everything's going to run slower, and that can be a problem. Maybe we have overfitting, all that stuff. So to get around that, instead of using an explicit phi, we're going to avoid phi altogether by using something called the kernel trick. The kernel trick is just sort of a computational thing in a way, but those are the two ideas that we're going to put together. We're going to see a huge boost in performance over the standard SVC. Okay, so let's start with just the idea of feature transformations, and let's start with a very concrete, though very simple example. So here's a data set that, as you can see, well, it's a little bit hard to see. These are some red samples out here. These are some blue ones here. There's no way I can linearly separate them. I can't pass a line through here in any way that separates them. So these are my original X. But now, what if I add a new feature, which is just the squared radius? So notice that this is the origin in this space. So if I add a new feature, which is the squared radius, which is x1 squared plus x2 squared, now in that new feature, so now you can see I have a three-dimensional, this is my new feature, x1 squared plus x2 squared. In this new space, I can pass a plane through here perfectly, separate my data. So it's sort of like in the original feature space, we were able to create a circular boundary by lifting up to a higher dimension and then putting a linear boundary there. So this is a very simple, very contrived example, but it sort of illustrates what we hope to have happen with practical data in maybe very high dimensions. All right. Okay, so that's key thing, higher dimensional space. Any questions on this? Yeah.
Do you have any other examples? I understand this, and you could change the center or the origin very easily by doing x minus for each. But I don't understand the last picture. How would you do a kernel trick for that?
Yeah, it's a good question. You need to have kernels that you trust that tend to work well in practice, and they're out there. There's a lot of theory and ideas about them. We're not going to dive deep into that. We don't have time. Except I'll show you what they look like. I'll show you more about it. But yeah, it's a good question. How, if someone just gives you a data set, obviously the transformation you want to use is going to be different than for another data set, right? So how do you choose your kernel? Or sorry, how do you choose your transformation?
Sorry, it's going to be really hard to visualize if you have more than two features.
Yes. And right, visualization is really tough for us once we go above 3 dimensions. So it's probably not going to be something that we can visualize, but maybe something that mathematically, if we're good enough, we can figure something out. But yeah, it's a good question. All right. Any other questions for now? Okay. So, but now there's sort of the catch, which is similar to the catch we saw in polynomial regression. You can add all these polynomial features, but then you have a lot more. It's a more complicated problem. But anyway, let's just say we want to do this. So how do we do this with our binary SVC? So here's the equation for for how we're going to train or find our optimal weights and biases, we have this cost function, and we just need to somehow minimize that. And it's a convex cost. We can do it with algorithms. It's not differentiable because of this max, so we can't do it with gradient methods, but it's not a big deal. It can be solved. sklearn, we saw how it solves it for us. But here's sort of the important part. The z, these are the scores. All we're going to do is where we used to have an x, or xi, we're going to replace that with phi of xi. That's our transform training feature. So this is all we need to do to train our model. And then once our model is trained, this is an equation that we saw on the slide with the alphas and where we tried to take gradients. It's just sort of a way of describing what's happening where we can see if you have a new test vector x, how do you actually get z or the prediction y hat? Well, we said what you can do is you can formulate this expression. So these alphas were a little bit strange, like they were some numbers that we weren't sure exactly how to compute them in one case. It turns out that if you know what you're doing, you can figure out what they are. They do exist. They are computable. We'll see in just a moment more on that. But the point here is that if you have this transformation phi, then all you need to do is transform your data, transform your new test vector, take their inner product, and then eventually you can compute your new test prediction. Okay, so it's all possible simply by transforming your training data and transforming your test features. So in theory, at least, it's possible. But the problem now is, what if the dimension of your transformation is very high? What if it's, you started with a few features and now you have millions or something, or maybe you started with many, many features and now you have way too many to deal with. So that's sort of the issue. If you try to implement a really good kernel, maybe you find that it's just too big to handle, or not kernel, but a really good transform phi. It's too big to handle. And there's another issue which might sound kind of strange right now. Like, what if we want to use an infinite dimensional transform? We're always starting with a finite number of features, but what if we want to transform that to some infinite dimensional space? So it's not something that we can actually handle computationally anymore, right? It's impossible. Our computers can't handle infinite numbers of features. It is something that you can imagine doing analytically. Like if you have a curve on the real numbers, that curve has an infinite, there's an infinite number of values you need to parameterize that curve. So it's something that you've seen before, but it's just, it's not something we can compute with. When we work with computers, we need to work with sampled representations, finite numbers of points. So these are the issues with trying to use an explicit transformation phi. But it turns out that there's a nice way around this. So the first thing we have to do is we have to rewrite our SVC in a slightly different way. So this probably looks really weird and crazy, but this is what we're going to do. Instead of trying to solve for the weights W and the bias B, we're instead going to solve for some Lagrange parameters lambda. And what we need to solve is this constrained optimization problem. So this definitely looks unfamiliar. It's kind of coming out of the blue. It turns out we don't really have, we're not able to derive this in this course. If you are interested in knowing more, you can look at section 12.2 of this textbook. It goes through the derivation, exactly where this comes from. If you've taken a course in convex optimization, it probably will make sense to you. If not, it might not make sense to you. So for our purposes, we don't really need to understand all the details here. But suffice it to say, this is another convex problem that we can solve. We can find the lambdas that minimize this. And once we found those lambdas, if we really wanted to know what were the weights and biases, they are computable using these equations. Now, this is optional because in this new framework, you don't actually need to compute the weights and biases. That's the key point. you forget about weights and biases, you just compute the lambdas, and that's all you need. And the interesting thing about the lambdas is that the lambdas, how many lambdas are there? Can you see from these equations? How many lambda i's are there? N, right? Whereas, how many w's do we usually have? How many w coefficients? D, right? So what we've done is we've traded something that depends on the number of features plus 1 with something that depends on the number of samples, training samples. That's kind of interesting. It's like we're really solving a very different problem. So the intuition here is that as I do my feature transformation with a higher and higher dimensional features, that will not change the complexity of solving this problem because this problem doesn't depend on the number of features, right? As long as you can compute this inner product here, that's going to give you for every I and j, that's going to be a scalar. As long as you can compute that, you can solve this problem without worrying how many features you have. Okay, so that's sort of the intuition. Now, you might notice that actually a lot of these equations might look really familiar from the slide we had where we were trying to take the gradients and we got like the weird question mark. It turns out that that all these equations written in terms of lambda are exactly equal to the other ones that were written in terms of alpha, except now we have c times alpha I. So in some sense, this explains what those question mark values of alpha I were. Whatever the lambdas are here, you divide them by c, and you'll get the alpha i's. And what's interesting is, notice that these lambdas are always between 0 and c. That means that the alpha i's, the corresponding alpha i's, would be between 0 and 1, which sort of makes sense because what we saw before is we knew some cases alpha I was 0, some cases it was 1. We had this question mark. Well, it turns out all those question mark values are somewhere between 0 and 1. That's what we can see here. So anyway, there are some connections between what we did before. But the main thing for you guys is you don't have to understand all the details here. Just understand that this is a different way to compute the SVC, where you avoid computing the weight and bias directly. Instead, you compute these Lagrange multipliers. And once you know them, you can use them to do detection. So you need to, let's say, compute this B star, which is sort of like a bias term. And then you compute this stuff, and you get your prediction. So this is your test vector x. This is your predicted sample y. So the point is, you can train the lambdas, and then you can apply them. And you really never need to deal with the weight vectors w, which are the things that are growing with the dimension d. Okay, so that's essentially the first part of this. So there's this, slightly different approach. And now, let's combine that approach with this transformation phi of x. So to use that approach, all we're going to do is wherever we see xi or xj, which is there, we're just going to replace that with phi xi, phi xj, phi xi, phi x, and so on. Okay. And that gives us these equations. Okay, so if you tell me an explicit feature mapping phi, then, as long as I can do all this, I can solve the SVC for those transformed features. But now the beauty of this is, notice that you always have things showing up in a particular form. It's always phi of one x transpose phi of another x. In the first case, it's xi and x, xi star, xi xj, but it's always like one x and another x. And so instead of, let's just represent that as some new function, we'll call it kappa, and this new thing is going to be called a kernel. And this kappa if you want to think about an explicit feature transformation, it's going to take this form. But now that we have it written this way, we can actually forget about explicit feature transformations and just directly implement this function. And that will give us more freedom. There's ways to define this function that would require us to have an infinite dimensional phi that work really well, but now maybe we won't need to actually compute an infinite dimensional inner product. We'll just be able to compute this directly. So that's the key. This is what's called the kernel trick. The kernel trick is basically saying, forget about the explicit feature transformation phi, just write each of these as a kernel between two different x's, and then implement the kernel. Don't worry about explicit phis, just compute the kernel itself. So only need to compute the kernel, never the phis. And this is called the kernel trick. Okay, so let me show you some kernels, and maybe things will make a little bit more sense. So the most popular one is called the radial basis function kernel. And all it is you take the difference between the two x's, so in this case, x minus x prime, you take the squared Euclidean norm, you multiply that by some so-called kernel with gamma, some number you have to choose, and you exponentiate it. So you e to that power. Okay, so that's the most popular one. Another one that's pretty popular is the polynomial. Here you take an inner product between your two raw feature vectors, and then you scale it, you shift it, and you take it to the dth power. D might be 2 or 3 or something. Another version is you take x transpose x, you put that inside a hyperbolic tangent. And then another option is if your kernel is just x transpose x prime, that's what we did before. That's the support vector classifier. That's using no feature transformation at all. That's called the linear kernel. So this is the SVC that we had before. And then generally speaking, these things tend to work a lot better than the SVC when you use a kernel that's nonlinear. And this RBF is usually works the best, most popular. Okay, so basically all these kernels, what they're doing is they're just different ways to measure a similarity between x and x prime, those two vectors. And there's different ways to define similarity here, but they're all things that the kernel value increases as x and x prime become more similar, right? So here you can see like when x and x prime are exactly the same, the difference is 0, and you get e to the 0, which is 1. Now for any other x and x prime that are not the same, the inside of this exponent is a negative number, which means it's going to be less than 1. So this kernel peaks when x and x prime are the same, the highest value 1. As an x and x prime get farther and farther apart, then this thing gets smaller and smaller. And it's sort of a nonlinear thing where the exponential, it dies off really quickly. So for when x and x prime are relatively close, you get a value that's significant. But as soon as they're sort of away beyond a threshold, then all of a sudden this kernel is tiny. And it's sort of, in the end, it's a way of measuring, like establishing what's called a local neighborhood around a point. Like if x and x prime are close enough, the kernel gives you, reasonable values. And as soon as it's sort of beyond a distance away, certain ball width away, then the kernel is tiny. It's essentially 0. So that's essentially what it does, and there's different ways to design these kernels, but in general, what you do is you just try the different kernels and you see which one works best with your data, but usually radial basis function is what people use. Yes?
Sorry, you probably said this and I just missed it, but what does x prime exactly represent?
The kernel always takes in two x vectors, two versions of x. So here, when you compute y hat, it's going to be the ith training sample and the test vector. over here you can see in this B star, it's the ith training sample, and in this case, I star is any support vector index you can use. Over here for training, it's xi and xj, which are just two different training samples.
Okay.
So this kernel always involves a pair of x's. You know, the exact pair depends on how it shows up. But I'm saying in terms of the interpretation, in all cases, the kernel is going to be measuring some sort of similarity between the two x's it's given. Okay. Guys have some questions about any of this? Questions? No? Yeah.
Are there any popular kernel tricks that involve more than just two features? Am I understanding that correctly?
Oh, these work for any number of features, right? So these vectors, x can be any dimension.
Okay.
So we can apply this to MNIST, no problem. Anything you want. Because this is actually very easy to compute, right? Euclidean distance between two vectors. Exponentiation, super easy. So computationally, this is super easy to do. Apply this. The main work then is solving this. So the complexity of solving this problem is basically going to be quadratic in the number of training samples. So as your training data set gets larger, it's going to take more time to run. But it's invariant to the number of features, more or less, as long as you can compute these quickly. So in this case, like computing this grows linearly in the terms of the number of features d. Like,
Is it ever popular to do more than one kernel trick on maybe the same or maybe different subsets of our X matrix?
using different kernels? I don't think so. I don't think that would work. Yeah. Okay, and so the last thing is this. If you tried to figure out, like, what is the phi, the explicit transformation that gives you the radial basis function kernel, it ends up being something that would require you an infinite number of dimensions in your feature space. So it's not exactly easy to show that, but one way to kind of think about it is if you do this series expansion of the exponential function, you can see that that involves an infinite number of terms. And the point of this is basically just that if you try to find the phi corresponding to the RBF kernel, it would require an infinite dimensional explicit transform. And we can't do that. But it's very easy to implement this directly in the kernel domain. So that's the beauty of the kernel trick. Okay. Some more questions on support vector. So this is what we call the support vector machine now, different from support vector classifier. Okay, so how do we implement this in sklearn? Well, there's svm.svc. It works just like the usual ones. You have to tell it which kernel you're going to want to use. So built into sklearn are the 4 kernels that I listed earlier, or you can define your own custom kernel. You just specify this function, and it will compute with that. Oops, sorry. You have to tell it the kernel width. All these kernels tend to have a width here. So that kernel width is typically an important parameter to choose. If you don't choose it right, this all doesn't work very well. You also, as always with the SVC, you have to specify the this C number, which controls the number of support vectors. And in this case, these two things have to be optimized together because they interact with each other. So as always, we want to optimize this stuff with cross-validation. There's a nice example in the sklearn documentation you can click on if you want. For MNIST, this is a pretty popular data set, pretty popular technique, so people have figured out what are the values of C and gamma that work best. So on this website, this guy is suggesting C of 2.8, gamma of 0.0073. We run this on MNIST, and we get an accuracy of 97%. So we went from 90.7 to 97, right? Huge jump in accuracy. So this is only using 10,000 samples. It's not using the full data set for training. We could do even better. But basically, this is where you finally get to see the SVC having true powers with this feature transformation implemented using the kernel trick for efficiency. And this does way better than multinomial logistic regression, SVC. So this is where we get a really good method in the end. And before neural networks got really popular in about 2012, these techniques were close to state of the art. This is what people were using. So, okay, I just got one more slide just to, you might ask the question again, okay, what if I have more than 2 classes? How do I train an SVM? And so, so there's sort of summarizing a number of things. So one thing you can always do is you can always try to do one versus rest. So, and okay, now scikit-learn doesn't give you all the options, so I'm going to try to explain the options that it gives you. So if you want to do one versus rest, actually the only technique that lets you do this is linear SVC, which is the one with the linear kernel, not this one that works really well. Okay, so that's your only option for one versus rest. We also saw that there's this Kramer-Singer option. That also is implemented in linear SVC only, and that only works for the linear kernel. So, and as we saw before, going from here to here, performance improvement, but a slowdown in the runtime. Now it turns out that this svm.svc uses something that's a little different from one versus rest called one versus one. So what it does here is it considers every unique class pair. So let's say I have 3 classes. Make a little table here. K equals 3. How many unique class pairs do we have? Well, we would have 1, 2, 3, 1, 2, 3. Like this would be 2 and 1, 3 and 1, 2 and 2. So those would be the 3 unique class pairs for three classes total. So for each of those unique class pairs, K and K prime, you separately train a binary classifier. And so in total, there's K times K minus 1 over 2 of these guys. And then with all those binary classifiers trained, there's a way of putting them together to get your final classification answer. So that is what is actually done in SVM SVC. And that is the one that can use a variety of kernels. But it is slower than linear SVC. So that's just the trade-off we have. But usually performance is way better, so you probably still want to use it. All right, any questions so far on this one versus one idea? Yeah.
Just for both one versus, so we trained multiple models, and you said there was some way that you come, when you want to make your prediction eventually, you have like a final classification maybe for a point?
Yeah.
What does that process look like?
So in the case of one versus rest, it's pretty straightforward. Because in one versus rest, what you're doing is you're essentially training this and this separately, and then next you're training the next 2. And so on. And by the time you're done training all those K things, you have these, right? So that's pretty easy to see what's happening. In one versus one, it's maybe not as easy to see how it's all going to be put together. But there is a way to put them together in the end to finally get what you need. So, yeah. So, yeah, if you want to learn more, probably, not sure, sklearn documentation might have some on that. But The very last thing is there's another nice formulation. So this is, okay, so we have here SVC, another nice formulation called new SVC. It will give you exactly the same answer in the end, but the interface is different in that instead of using C, which is a number that's a bit hard to choose because it could span many orders of magnitude, you use this number nu, which is always between 0 and 1, and can be interpreted as a lower bound on the fraction of support vectors. So what I mean by fraction of support vectors is like number of support vectors over total number of training samples. So when you set, nu to 0.5, you know that the number of support vectors will be at least 50% of your total training size. If you set nu at 0.7, then number of support vectors will be at least 75% of your training size, and so on. So it just gives you a much more direct way of choosing this parameter C, or let's say more interpretable. You know it's always going to be in that range. You know how to interpret it. But at the end of the day, if you're going to do like a grid search or something and it's a good grid search, you should get the same kind of performance with those two methods. Okay, so that's so that's all we have for the SVM. Any questions on SVM? Yeah.
So when we make a new dimension, is that analogous to adding another feature that is like a function of our existing features?
Yes.
And could you use another type of regression with that new feature to get improved results ever?
You can always, there's always other types of regression. So we've learned about, for classification, we've learned logistic, we've learned SVC. We're going to learn about tree methods later. That will give us another, method. We're going to learn about neural networks. That will give us another method. So yes, you could use any of those methods you want. But then the fundamental question is, how exactly do I get my new features from my raw ones, right? How do I come up with that phi function? But the other thing to remember about the SVM and the kernel trick is you're not actually explicitly coming up with a phi function. Your kernel is explicit, and the phi function is this weird thing where you don't even necessarily know what it is, right? Like in this radial basis function kernel, the phi function is infinite dimensional. It's hard to get a handle on that. But the kernel function is very explicit. Okay, great. So we have just a couple minutes left, and let me just start Unit 8, just the very beginning, because we're kind of at a very good place to understand what we're going to do next. So this unit is going to be on neural networks. And the key question that neural networks are going to answer for us is, how do we choose the feature transformation? So we're going to return to the notion of a explicit feature transformation, not a kernel, not a kernel trick stuff. This is an explicit transformation, phi of x. And the question is, if in general we don't know one, can we actually learn one from our data itself? Like, let's not just choose an off-the-shelf one. Let's actually try to figure out directly from the data we're given. And that way, it can adapt to the data. And if we do a good job, it will work really well with that data. So that's the beauty of this new approach that's different. It's similar to our SVC or SVM in that it's some transformation followed by some linear classifier. But now, the transformation is going to be learned rather than off the shelf. And we'll show how this works for a simple data set. So like this data set, as you can see, green points in the middle, blue points on the outside. It's not linearly separable. But we're going to talk about a very specific way to generate some intermediate features, which is going to be based on what we learned with linear classification. We're essentially going to cascade two stages of linear classification. The first stage of linear classification involves these boundaries, and it will give us some features, probabilities, you can think of them as that. The probability that your data point is on this side versus this side, And in this case, we're going to get 4 different probabilities. And then we're going to take those as the features for our next linear classifier. And it's going to give us finally a really nice output. So this is like red means the probability of being in the green class, white probability of being in the blue class. And you can see it's doing a pretty good job classifying this data, right? And it learned these things directly from the data itself. All we did is we set up the idea of let's do 2 stages of linear classification, but we didn't tell it how to place these lines. It figured that out itself from the data. So that's a 2-stage neural network. And we can, of course, generalize this to more stages, but in this unit, we're going to focus on the 2-stage because there's plenty to learn in 2 stages. And then in Unit 9, we're going to generalize it to many stages, deep neural networks. And we'll get into all the sort of new problems and new challenges and new things we have to do in that case. But that's what we're going to study next. I think it's a pretty exciting time in the semester because we're going to get to kind of assemble all the stuff we've done until now to come up with some really powerful methods, very general, very powerful, that are based on learned transformations. All right, so see you guys on Friday.